in 9.1, what we tested was the chi-squared test for independence. We wanted to see were two categories dependent or independent, okay? And that's what we used the test for. We said, okay, test at the 1% level, are these two categories independent of each other? And if they're not, then they're dependent. So we're going to be doing the exact same mathematics, the exact same calculations, the exact same hypothesis testing, but this time we're testing how good of a fit is the observed data with the expected data. So how good of a fit? For example, let's say that you have a six-sided dice and you want to test whether or not it's a fair dice. Your expected values would always be 1/6 of the number of rolls that you have. If you rolled the dice 600 times, you would expect to get 100 ones and 100 twos and 100 threes and 100 fours if it's a fair dice. And so you have a theoretical expectation, and what we want to do is compare that with the observed or the experimental results and how good do they fit together. And so this is called a goodness of fit. And so what we're going to do is our null hypothesis is that the observed data is consistent with the expected data, that the experimental observations match the expected observations or the expected values. The alternative is that they're not consistent. The theoretical does not match the experimental. And then we're going to state our significance level. We have to have expected frequencies greater than or equal to 5. We're going to take the observed frequency and the expected frequencies. And in this case, what we're going to do is we're going to take the expected frequencies, and that is going to be the number of items multiplied by the p-value, the probability of success, okay? And this is something that's a carryover from the last chapter, this p-value probability. Our test statistic, once again, is chi-squared. Once again, to calculate it, we're going to subtract the observed from the expected, square it, and divide by the expected. So this is something that we just got done doing. The chi-squared calculation squares the difference. So chi-squared is always positive, and it's always right-tailed. And we talked about this earlier in 9.1. Once you have that chi-squared value, you can either use a web page, Desmos, or Google Sheets in order to calculate the area under that curve. You're going to be using Google Sheets with chi-dist. In this case, the degrees of freedom is equal to k minus 1. So the number of items that you have minus 1. Then you run your conclusion. You compare your p-value to your significance level, and you say, we either reject the null hypothesis or we fail to reject the null hypothesis, and then you state your results. So let's say that you have a random dice and you roll it 500 times, and the frequency of each number is recorded and put into a table. So here's the frequency of each number. So you rolled 78 ones and 87 twos, and the question is this a fair die? Does the observed frequency match with the expected frequency at the 5% level? So you can see this is almost identical to what we did in 9.1, okay? So state the null and alternative hypothesis. We got that. The null hypothesis is that it's consistent. The alternative is that it's not consistent, and we're testing at the 5% level. We do have a random sample taken, and the frequencies are greater than 5. So that means good, we can proceed. So if you were rolling a six-sided dice, how many ones would you expect? Well, the probability of rolling a 1, if it's fair, is equal to the probability of rolling a 2, rolling a 3, 4, 5, and 6. So that's 1 out of 6, right? And so the probability of each number is 1 out of 6, or 16%. So we're going to take our 500 rolls, and we're going to multiply it by 16%. So we would expect there to be a frequency of 83.3 of each value. So here's our table. How many ones did we roll? 78. What was the expected? 83.3. How many twos did we roll? 87. What was the theoretical expected number of twos? 83. Okay, so this is our observed, this is from the experiment, and this is our theoretical. So we have experimental and theoretical. Okay, now what we're going to do is we're going to subtract them, then we're going to square that number, then we're going to divide it by the expected. And so this is the calculation that we need for chi-squared. And we're going to add these up. And that will give us chi-squared. So now our degrees of freedom are equal to 5. So we're going to have some kind of squirrely chi-squared graph. And we are going to plot 1.5046 blah, blah, blah on that graph. And we are going to find the area to the right of that graph. Using Google Sheets, we use the chi-dist formula, and we get an area of 0.9126, which is about 91%. That is way above our threshold. Using Desmos, this is what the graph looks like, 0.91. You can see that that matches up with Google. And so our p-value is much greater than the significance level. So we fail to reject the null hypothesis. So we fail to reject. So the observed frequencies are consistent with the expected frequencies, which means the dice is fair. So there's not enough evidence to show that the dice is not fair. So we fail to reject the null hypothesis, which means it's a fair die. That these results, this distribution of our experiment at the 5% threshold matches or is consistent with the expected theoretical distribution.